Okay. It's my pleasure to introduce Professor Farmer Schlutzenberg from TU Vienna. Professor Schlutzenberg is a winner of Frontiers of Science Award, and he'll talk about the axiom of choice and large cardinals.
Okay, so first of all, I'd like to say thank you to the organizers for putting together such a fantastic conference with hard work, and thank you for the opportunity to talk today. Okay, so I'm going to overall talk about these things. So first of all, the set theoretic universe V and the axiom ZFC for set theory, large cardinals and elementary embeddings, and the determinacy, a little bit about determinacy, and then at the end, the main sort of focus we'll get to is large cardinals, which violate the axiom of choice. Okay, so beginning with just the axiom of choice. So recall that the axiom of choice asserts that for every family F of sets, non-empty sets, there is a choice function for the family. So that's a function which selects, for each member of the family, selects some element of the family. So formally, it's a function C that maps the family F into the union of the sets in the family. And for every X, set X in the family, we have, it doesn't work, okay. We have that C of X is an element of X. Okay, and so the axiom of choice is a basic assumption for mathematics, and it's essential in lots of proofs, and if we didn't have it, mathematics would look very different in general. So it's really important. Along with these applications, there's a lot of surprising and unintuitive consequences, like the Bernard-Tusky paradox and so forth. So it has sort of these two sides to it. Yeah. Okay, so the ZFC axioms are the standard axioms for set theory. It stands for the Zermelo-Fraenkel axioms with the axiom of choice. C stands for choice. And so these are axioms like the axiom of union, power set, infinity, separation, and so on. So it doesn't matter exactly what these are in detail, but they just basically give us lots of properties that we know hold of sets in the universe of sets. And so, yeah, so they describe the essential features of the full universe for of sets. Yeah, so they are powerful enough that they can build a foundation for standard mathematics based on them. Let's write it this way. Yeah. If we remove the axiom of choice, then the remaining axioms we write just as ZF. And the ZF axioms are all intuitively constructive. So I don't mean in the formal sense of constructive mathematics, but that they all, I mean, roughly they assert that given some certain sets, we can construct some other sets in a reasonable fashion. Like, so the axiom of union just says that if I've got a family of sets, then I can form the union, and the union itself is a set. And that's sort of clearly prescribed from the given family. The axiom of choice is different to these. You know, if you look at the statement was that for every family, there is a choice function that's given by it, but the choice function is not uniquely determined in any way in general. So it's sort of just stating there is this object, but there's no specific manner to construct it. Okay, so it's somewhat of an outlier compared to the other axioms. Although ZFC gives a good foundation for mathematics, it is incomplete, so very incomplete. There's a lot of questions that it doesn't decide answers to. So for example, the basic properties of the projective sets of reals, and I'll remind you in a moment what the projective sets are, but they're some sort of simple sets of reals. So ZFC axioms do not tell us whether all projective sets are Lebesgue measurable, whether they have the Baire property, whether there's a projective well order of the reals. So these are basic questions it just doesn't tell us. Other things like cardinal arithmetic, like whether the continuum hypothesis holds or not, and combinatorial properties of the reals, like if we have a collection of Lebesgue measure zero sets and we take their union, when is that still Lebesgue measure zero? That's not in general decided by the axioms. Okay, so and there's a bunch of other sorts of things as well. So just to remind you what the projective sets are, because this will be a nice example of some things later on. So the projective sets are just sets of reals or reals to the n for finite n, so n-dimensional Euclidean space. And the projective sets are just the smallest collection of sets P, such that P has these three properties. P contains all the Borel subsets of all finite dimensional R to the n. It's closed under complement inside each Rm, so if we've got a subset of Rm that's projective, then so is its complement in Rm. And it's closed under projection to smaller dimensional spaces. So the way I get a projective set is I start with the Borel set, project to some smaller subspace, take the complement in that subspace, project again to a smaller space, and take complement and so on finally many times, and that generates all the projective sets. So they're all produced in this sort of simple fashion. Okay, so as I said, ZFC is incomplete. So then a natural question is, can we complete it by adding more axioms? We know by Gödel's theorems that we cannot complete it, at least not in any computable fashion. So there's no computable list of axioms that decides all the statements, as long as they're consistent. So the answer is no there, but we can try to at least partially complete it by and hopefully answer many problems, maybe all natural questions or something like this, or at least a lot of them. Right? So we can look for a better system. So ZFC is supposed to describe the set-theoretic universe. So an associated question is, what are the properties of the true set-theoretic universe? What should we expect? And so here are two guiding principles that I want to adopt for seeking a better axiom system. So first of all, the set-theoretic universe V should incorporate all structure, all mathematical structure. It's supposed to be the full set-theoretic universe, so it should contain everything. And the axioms should be natural in some sense. So of course that's subjective, but when one has the system and looks at them, in the end they should be reasonably natural, not just ad hoc and random. Okay, so these are two principles I want to use. Okay, so I want to now just give the basic picture of the set-theoretic universe as a structure, and that's built along the ordinals. So as a reminder of ordinals, ordinals are linear order such that every subset of it has the least element, and non-empty subset has the least element. And here's some of the basic ordinals at the bottom. We start with the non-negative integers, 0, 1, 2, 3, and so on. After all of the integers, we reach the first infinite ordinal, which is omega. And then after any ordinal, we can add 1. So we have omega plus 1, omega plus 2, and so on. We go through all of those until we get to omega plus omega, or 2 times omega, or in the usual notation, omega times 2. I have the wrong way around. And then we keep adding 1 until we get to 3 times omega, 4 times omega, and so on. Pass through all them until we reach omega squared, and so on. So these are the first few ordinals. Ordinals come in 3 types. There's 0, successor ordinals, and limit ordinals. The successors are when we've just added 1 to some previous ordinal, and the limits are the other ones like omega, 2 times omega, omega squared, and so on. Okay. And one other property of an ordinal is any ordinal is the set of its predecessors. So omega in particular is the set of the finite ordinals, the n's, so it's the set of natural numbers. So omega equals the set of naturals. Okay, so here's the picture of the set-theoretic universe. We draw it with a big V shape, and we also use the variable V to denote it. And so the universe is a whole bunch of sets, and they're stratified through this what's called the cumulative hierarchy. So that's some sets, the V alphas, where alpha is an ordinal. And at the bottom, we start with V0, which is just the empty set. And given any V alpha in the hierarchy, we get to the next level by taking the power set of it. So this equation here, V alpha plus 1 is the power set of V alpha. So remember the power set, any set X is just the set of all subsets of X. Okay, so starting from the empty set, we take the power set to get to V1. And so the power set of the empty set, there's only one subset of it, which is the empty set itself. So V1 is just the singleton with the empty set in it. And then V2 is the set of all subsets of that. Well, there's 2 subsets of that, the empty set and the full singleton. So V2 has those 2 elements in it. And then V3 is the power set of that, which has 4 elements, and so on. So we go through the Vn's by taking those power sets. The omega, the first infinite stage, is then defined as the union of the previous stages. So for every limit ordinal in this process, we take the union of the previous stages. And so V omega is the first infinite stage of this hierarchy, and it's countably infinite and contains all the natural numbers. V omega plus 1 is its power set. That's uncountable, contains all the real numbers. We think of real numbers as being sets of natural numbers. Okay, and that just continues all the way through with the same power set at successive stages and unions of limits. And that gives us an increasing hierarchy. We have V alpha, a subset of V beta for all alpha less equal to beta. And then the ZFC or even ZF axioms prove that the universe V is the union of all of these things. So V, every set is in this union, and so V is the full universe of all sets. Okay, so this is the picture of V, and it's what the ZFC axiom should be describing. Okay, so now large cardinals. So the axiom of infinity So it's essentially that omega exists, that the set of natural numbers exists as a set. And large cardinal axioms are variants of the axiom of infinity, which assert that larger infinite sets exist. Okay, so the sets that they guarantee are somewhat intuitively large or complex sets, so maybe infinite sets with certain complex structure, and they're sort of beyond the infinity of the natural numbers. The large cardinal axioms tend to strengthen the certain principles that are in the ZF axioms, like that give hierarchy and closure principles coming from the ZF axioms. So they have a style that's somewhat similar to them, and so they have sort of a natural connection to the ZF axioms. They answer a lot of key questions, like some of the questions that I listed earlier. I'll mention examples later that are not resolved by ZFC by themselves. And in practice, if we have two large cardinal axioms, then they can be compared in terms of various ways, but in particular in terms of consistency strength, which is a natural measure of the strength of a set theoretic proposition or theory. And so they sort of, in practice, they line up, and so we have a coherent sort of picture of a whole bunch of axioms that fit together in this hierarchy. So it looks like a natural object. We're not choosing sort of some random different ones that violate each other. Okay, and so this leads to them being some sort of natural candidates for what we want for completing the ZFC axioms. Okay, so I'm going to give two examples of large cardinals to give the basic point of them. So first of all, a cardinal kappa is an inaccessible cardinal if roughly that it's not reachable from below, like from sets of smaller cardinality, by forming power sets or by forming unions. Okay, so formally, so a cardinal kappa we have, so a cardinal is just an ordinal which is not in bijection with any smaller ordinal, so it's like the least ordinal of its size. And so if I've got a cardinal kappa, then we say it's inaccessible if it's got these two properties. So first of all, that for every cardinal strictly smaller, every cardinal lambda strictly smaller than kappa, 2 to the lambda is also smaller than kappa. So it's closed under this 2 to the lambda operation. 2 to the lambda is just the cardinality of the power set. So it's saying it's not reachable by power sets. And then secondly, kappa is not the union of fewer than kappa many sets, each of which have cardinality less than kappa. So if I've got a family of sets of size less than kappa, and everything in the family is size less than kappa, then the union is also size less than kappa. Okay, so it's not reachable by these two things. That's an inaccessible cardinal. I'm going to state a simple fact about the relationship between inaccessibles and ZFC. For that, I just want this notation. M satisfies V. So this is just here. The M here is some mathematical structure. The satisfaction symbol is this symbol in the middle, and phi is some statement or theory it could be. Okay, so it just means that the statement phi is true when it's interpreted in this structure M. So for example, if M were a group, now I'm calling it G, so then a group G is abelian if and only if it satisfies this statement that the group product is commutative, so for all x and y, x product y equals y product x. Okay, so that's what this symbol is saying. So the group product here refers to the group product in the sense of this group G, and the for all xy refers to the ranging over the elements of the group. Okay, so that's its notation. And so we have a theorem, if kappa is an inaccessible cardinal, then we can look at V kappa, this level of this cumulative hierarchy. Well, that level satisfies all the ZFC axioms already. So we have by assumption we have ZFC in the full universe V. If you cut it off at V kappa and interpret and sort of only look at the sets down inside V kappa, ignoring all the other stuff up there, then you get a full ZFC model right here. So you could do all of the standard mathematics inside that V kappa. And not only that, there are many V alphas, alphas less than kappa, where you also get the V alpha model in ZFC. So we get a whole lot of ZFC models. And you can't prove that in ZFC alone. ZFC alone does not prove there are P alphas or even any set models of ZFC by Gödel's incompleteness theorems. And so this having a ZFC plus an inaccessible cardinal is strictly higher in this consistency strength order than ZFC. Okay, so that's what we have there. So this is the notation, right? That V kappa satisfies ZFC. It just says that it satisfies all the axioms in ZFC. Okay, so here's a list of some of the large cardinals in the large cardinal hierarchy. So I mentioned already ZFC and inaccessible cardinal. I'm going to tell you in a moment what measurable cardinals are. But then there's all these other ones here as well. So below ZFC, we've just got Peano arithmetic, the basic theory of the naturals. And then in between ZFC and inaccessible, there's ZFC plus certain kinds of models of ZFC exist. And then there's all the other large cardinal notions above here. So it doesn't matter right now what the definitions are, but I'm just wanting to point out that there's a whole lot of kinds of large cardinals, and they're arranged. This is increasing in the consistency strength hierarchy, and there's a whole lot of structure in there and detail. And actually, in between each of these large cardinal notions, you can define other intermediary large cardinals which sit between them, and there's a whole lot of structure in there as well. And so it's just very detailed and rich, the hierarchy. Okay, so this is some evidence that it's a natural hierarchy to look at. Okay, so I want to define what a measurable cardinal is next, and for that we use elementary embeddings. Okay, and so here, this is elementary embeddings we'll be thinking of as structure-preserving maps between models of ZFC. So it's similar to if we have a group homomorphism between two groups, something like this. Okay, but here we're dealing with universes of set theory. Okay, so if we've got M and N are two models of ZFC, so that each of M and N have their own cumulative hierarchy, and they look like this sort of collection, some sort of collection of sets like that. Then we want to say what it means for a function. So we've got a function J from M to N, and we want to say what it means for that function to be an elementary embedding. And that's just that it preserves basically everything in the language of set theory about sets. So we have that for every formula phi in the language of set theory, and for all parameters x1 to xn that you can take from M's universe, M will satisfy that the phi holds of those parameters if and only if N satisfies that phi holds of the images of the parameters under the map. Okay, so that's an elementary embedding. And it's every phi in the language of set theory. So in particular, the simplest kind of thing we can say in the language of set theory is just set membership. So for example, M will satisfy that x1 is in x2 for two given sets, if and only if N satisfies J of x1 in J of x2. So that's one property that would be true. But you can also make much more complicated statements in language of set theory. I mean, not very complicated one, for example, would be x1 is equal to the intersection of x2 and x3, if and only if N satisfies Jx1 is the intersection of Jx2 and Jx3, and so on, with these sorts of statements. Okay, so this is an elementary embedding. Okay, and measurable cardinals come from special types of elementary embeddings. So one thing we want is that we deal with transitive structures M and N. So a set or a class is just like a big collection of sets that need not be a set, but it's similar to a set. So a set or a class M is transitive if it's closed downward under set membership. So that just means that whenever you've got X an element of Y and Y is an element of this class M, then X is also in M. It's just closed downward. Okay, and so now if I've got two transitive universes M and N, probably the M and N here are models of ZFC here, then and if I've got an elementary embedding from M into N, then we define the critical point of the elementary embedding to be the least ordinal kappa here, such that J of kappa is strictly bigger than kappa. Okay, so you can show, I mean, in general, for what I've written here, there might not exist a critical point, but if it exists, then this is the definition. You can show that whenever you've got an elementary embedding between transitive structures like this, then J of every ordinal alpha is at least, J of alpha is always at least as big as alpha for all ordinals alpha. So if there's any point where J of alpha is not equal to alpha, then you look at the least one, then it has to be like this, that J of kappa is strictly bigger than kappa, and below here they're just fixed. Okay, so that's the critical point, and that leads to a measurable cardinal. So a measurable cardinal is just an ordinal kappa, which is the critical point of some elementary embedding, J, where the domain of the elementary embedding is the full set theoretic universe V. So that's a key thing in there. So we have now, instead of just arbitrary M and N, we've got the full universe V, so I'm mapping the entire universe into some M, and where M must be transitive, and M is a subclass of V. Okay, so really in the picture, I've drawn them as two separate structures here, which they are, but M is really, it could be seen as sort of a sub-universe of V, so it sort of, in some sense, should sit inside here in the diagram. Okay, but the properties of V get reflected into properties of M when we consider properties in M. Okay, so that's a measurable cardinal. The critical point is such an embedding. And we have a similar theorem here between measurables and inaccessible cardinals, analogous to what we had from inaccessibles to ZFC. Okay, so if kappa is measurable, then also kappa is inaccessible, and there's cofinally many alphas less than kappa which are inaccessible. So I get a whole lot of inaccessible cardinals. And remember that below every inaccessible cardinal, I've got all these models of ZFC. So I'm building up this very nested structure of all of these models of ZFC, right? And so that means that all the standard mathematics can be done down here where there's some first level of ZFC. And in fact, even in a ZFC model, the real numbers and sets of real numbers and stuff all occur right down in V. V omega plus 1 has all the reals, V omega plus 2 has all the sets of reals. So if you're looking at these sort of standard objects, they occur right at the bottom, right? And I've got then all these large cardinals which look like they're irrelevant to the structure of reals and so forth. So that's sort of the picture. Okay, so similarly we have, a measurable cardinal is strictly higher in consistency strength than an inaccessible cardinal because of this picture. Okay, I want to mention one bit of the proof of this theorem here, just to give a flavor for what happens with large cardinals. So I want to prove that if kappa is measurable, then there is an inaccessible less than kappa. I'm going to assume the bit that kappa is inaccessible. So suppose kappa is measurable and it's inaccessible, and let's prove that there's an inaccessible cardinal alpha less than kappa. Okay, so here's my elementary embedding, critical points kappa. That's what I have to start with. So now we first observe that because kappa is an inaccessible cardinal, M also thinks that kappa is an inaccessible cardinal. Okay, so that's not using the elementarity of the embedding. The elementarity would say that because kappa is inaccessible here in V, J of kappa is inaccessible in M. Okay, kappa itself here is not in the range of the embedding, so it's not elementarity. What it is that, suppose kappa was not inaccessible in M, then M thinks that kappa can be reached from below by either power set or union. So say it's reached by power set, that says that I can get some lambda less than here and a surjection from the power set of lambda onto kappa. M thinks that happens. Okay, but if you take such a surjection, I can look at that object from the point of view of V, and it's still a surjection from, in V also thinks it's a surjection from the power set of lambda or some subset of the power set of lambda onto kappa. And that contradicts that kappa is inaccessible in V. Okay, so the fact that this is because M is a sub-universe of V, it's all contained in there. Okay, so that tells us, this argument tells us that M also thinks that kappa is inaccessible. Okay, but notice kappa is less than J of kappa. So M thinks that there is some inaccessible cardinal which is less than J of kappa, namely kappa is inaccessible less than J of kappa. Okay, and that statement has only one parameter, which is J of kappa. Okay, there is, I'm getting rid of kappa from the statement, just that there exists an inaccessible less than J of kappa. So that's a statement about J of kappa. So that statement pulls back to V under the elementarity now, that V has to satisfy the same statement about the preimage of J kappa, which is just kappa, so it thinks there is an inaccessible less than kappa. Okay, so that's a typical kind of argument using elementary embeddings. Some properties of kappa can be reflected below kappa down to smaller alphas, coming from the fact that we've got this elementary embedding. Okay. Okay, so although these large cardinals sit way above things like the reals and sets of reals, it turns out that the large cardinals have a whole lot of influence over the reals. Okay, and so, for example, this is a very nice theorem. If there are infinitely many wooden cardinals, so wooden cardinals are higher in consistency strength than measurable cardinals, but that's okay. So these are some large cardinals. If there are infinitely many of them, then the theory of the projective sets is determined much more than just from ZFC. All projective sets will be measurable and have the property of Baire, and there's no projective well order of the reals. Okay, so just from these wooden cardinals which sit way high up, we get like the projective sets are suddenly really well behaved. Okay. So yeah, so even though they look like they're sort of nothing to do with the reals, they have an interesting influence on them. I want to mention something about the proof of this, which is that it goes through the axiom of determinacy or partial axiom of determinacy. Okay, so I want to quickly mention this. So determinacy deals with certain kinds of games played between two players. So if I've got a set of reals, and here I'm thinking of set A of reals, and I'm thinking here of reals as being functions from naturals to naturals. Then we have an associated two-player game, G sub A. In that game, there are two players, players 1 and 2. And players 1 and 2 alternate playing integers in the game through infinitely many rounds. So player 1 plays an integer x0, and then player 2 plays an integer x1 in response. Player 1 responds with another integer x2, and so on. We go through infinitely many rounds, and so we end up with an infinite sequence of integers x. X is this full sequence. And then we just declare at the end that player 1 wins the run of the game if x, this sequence, gets into the set A we had at the beginning. So A is this set of functions. Both the players can see the set. They know, player 1's trying to make this real end up in that set. Player 2's trying to avoid it. And they can see what the other player's playing as they go along. And that's sort of the situation. Okay, so we say that the game A or G sub A is determined if there is a winning strategy for one of the players in the game. So the winning strategy has got to be a function which tells you at every possible position how to play your next move, and it has to guarantee a win no matter how the other player plays. Okay, so that's when things are determined. And this theorem about wooden cardinals and the projective sets factors into these two pieces. So first of all, if there are infinitely many wooden cardinals, then all projective sets of reals are determined. All the projective games given by projective sets A are determined. And if all projective sets are determined, then they all have these nice properties, the Beck measurability and so forth. And so this is how the large cardinals sort of affect the sets of reals, is really through determinacy, and then determinacy has this influence on their properties. We can define the axiom of determinacy, which just says that every such game is determined, or for every set of reals. So the previous theorem just talked about the projective sets of reals, but we can talk about arbitrary ones. Okay, well, this axiom is false because there just is an undetermined game. Using a well order of the reals, it's straightforward to construct a game for which there's no strategy. But you do need the axiom of choice there in that proof. And so we could also restate the theorem in this way. So if we consider the theory ZF plus AD, so the ZF axioms without choice, add the axiom of determinacy, this proves that the axiom of choice is false, because otherwise you have ZFC, and then you get AD false. So this is just a restatement. If I here the axioms in the background for theorem 0.19 is ZFC by default, but here I'm changing it to ZF plus AD instead. Okay. Although that axiom of determinacy contradicts choice, it proves certain fragments of choice. Okay, so like for example, if I've got a countable family of sets of reals, then for such families there is a choice function, provably from AD. So AD gives us like weak fragments of choice, provably. Okay, and large cardinals, we already mentioned that if you have infinitely Woodens, then projective sets are determined. Another result of this one of Wooden is that the theory ZF plus AD is equiconsistent with the theory ZFC plus infinitely many Wooden cardinals. So ZFC plus infinitely many Wooden cardinals does not prove ZF plus AD itself. I mean, it can't because you have choice, but they're equiconsistent, as in one theory is consistent even only if the other does. So they're equal in consistency strength. Okay, so there's lots of interactions between these large cardinals and determinacy. So I mentioned some basic properties of large cardinals earlier, sort of what they are and so forth. Well, one extra property to add to that list is that there's these intimate interactions with determinacy axioms. So there's a whole lot of structure in these things. Okay, I just want to quickly mention Gödel's constructible universe. So this is the least transitive model of ZF, which contains all the ordinals. And this is provable in working in ZF. So starting from ZF in the universe V, I can prove that there is this inner model L as the sub-universe of the universe, and it contains all the ordinals, and it's the least one. Okay, the way it's defined is not like I gave a definition here that characterizes it, but there's another definition that Gödel used, which builds up L sort of level by level through a hierarchy of sets L alphas, similar to the cumulative hierarchy for the V's, but using instead of taking full power sets at successor stages, one uses a restricted kind of power set, just adding a small number of subsets at the previous level to get to the next level all the time. So that's sort of how L is built initially, and then one proves this what I've stated as the definition here. Okay, and Gödel proved that L models the full ZFC axioms plus the generalized continuum hypothesis. So that gives consistency of these things relative to ZF. And not only, so that's ZFC, right? So this is working in ZF. We can build L, and L models the axiom of choice without assuming the axiom of choice in V. Not only do we have choice there, but there's a very explicit and definable form of the axiom of choice which holds inside L. So it's like a very choicey universe. And moreover, the theory ZFC plus V equals L, which V equals L just asserts that every set is in L. Every set is constructible, it gets into this universe. That's a very complete theory, as in it decides much more than just ZFC does alone. Certainly it can't be fully complete, of course, if it's consistent. And there, as far as I know, also though we don't know of examples of. There's. Okay, so ZFC plus V equals L does not decide statements like there exists an inaccessible cardinal. It's not decided, but statements which sort of come from other areas of mathematics. I don't know that we know of examples where this is not decided for that. I might be wrong about that, but so it's deciding a lot of things. Okay, compared to ZFC by itself. Okay, so this could make it a reasonable candidate for what we're looking for, which is completing ZFC, right? Well, but let's consider large cardinals. So L can exhibit small large cardinals. However, it satisfies that there are no measurable cardinals. So there's this straightforward proof that no measurable cardinal is in L. So L thinks there are none. And in fact, if there's a measurable cardinal in V, then the set of reals in L is countable. Okay, so L certainly thinks that it has uncountably many reals, because that's the theorem of ZFC. But if we look at it from the point of view of V, from the outside, then V has an enumeration of L's reals in countably many. And so V has many more reals. And so this means V is far from L. Okay, so a measurable cardinal says L is very thin compared to the real set theoretic universe. Okay, so the question was, should we adopt the axiom V equals L to use to complete our ZFC? Well, we have these two guiding principles that V should incorporate all structure and axioms should be natural. And well, this axiom system, ZFC plus V equals L, is reasonably natural. V equals L is a reasonable axiom to adopt. It's only one new statement. It's not like we're putting together some random collection of statements. So I think 2 is fine here. But 1 is that we should incorporate all structure. And we've seen that large cardinals are natural kind of structure. So these should be incorporated as well in V. And so L cannot accommodate it, so we conclude from that V is not equal to L. We should not adopt V equals L. Okay, so now going to get to sort of the main point of the talk, which is large cardinals which violate axiom of choice. So large cardinals beyond the level of at measurability and beyond are typically exhibited by elementary embeddings from V into some transitive universe M. And we get, so to get large cardinal notions which are strictly bigger than measurability, we can generate them from this sort of scheme by requiring that some sort of approximation between M and V. So requiring that M is closer to V in some sense. So for example, we can require that require some large ordinal lambda to be such that V lambda is a subset of M. So lambda, say, above the critical point of the embedding, and we require that V lambda is a subset of M. So this will increase the notion of large cardinal notion we get, and this leads to the idea of a strong cardinal. Similar, or a variant of that is that M is closed under lambda sequences, and that leads to the idea of super compactness. Okay, so this is how we can get stronger large cardinal notions. So the strongest approximation of M to V is just setting M equals V, and so this suggests that there's an ultimate large cardinal notion considered by Reinhardt, which is a Reinhardt cardinal, which is the critical point of an elementary embedding from V into V. So setting V equal to M over here. Okay, so this seems like, okay, we've got this hierarchy. If we go through the large cardinal hierarchy, it appears that it's increasing and very natural, and there's this natural notion of making M closer to V. So it looks like a natural ultimate large cardinal notion that should make sense. But surprisingly, it turned out that there is no Reinhardt cardinal. That Kunin showed in 54 years ago that this is just inconsistent. And his proof had two parts. So the first part is that if you've got an elementary embedding from V into V, and kappa is the critical point, then there is some lambda strictly above there, which is fixed by J. So J of lambda equals lambda. So it looks sort of like we have a kappa, and if you send kappa up to J of kappa, and then apply that again, J to J of kappa, you get J of J of kappa. And if you do that infinitely many times, you get up to an ordinal, the supremum of that, you get up to an ordinal lambda, which you can then show is fixed by the embedding. So J of lambda is equals lambda. Okay. And then it follows by elementarity that J fixes the next few ordinals. So J of lambda plus 1, J of lambda plus 2, and so on are also fixed. By the embedding. So I have this. And then if we consider J restricted to V lambda plus 1, V lambda plus 2, and so on, then it actually gives us an elementary embedding to that level of the cumulative hierarchy. So I get an embedding which looks like here's V, and I'm going to look at V lambda plus 2 here, but it's the same for any V lambda plus n. So I've got lambda plus 1 here. The embedding shifts ordinals below here, but then it fixes lambda, and I get an embedding like that from V lambda plus n into itself for any n. Okay, so that just, that's a straightforward thing to see. Okay, secondly, and this part is subtle to prove, but the proof is not too long. There's simply that there is no ordinal lambda and an elementary embedding from V lambda plus 2 into itself. So this thing here just does not exist. Okay, and so that shows that you can't have a Reinhardt cardinal. And in fact, sort of that, it's kind of odd because from the Reinhardt cardinal you get V lambda plus n into itself. You get all these embeddings up here, but actually there's a problem already at V lambda plus 2 that just kills it. Part 1 uses just ZF here directly, but part 2 makes it very important use of the axiom of choice. Okay, so there's an infinitary combinatorics that comes up to show that this is false, and that uses the axiom of choice. And he mentioned that it's not known whether ZF suffices for the proof. Okay. So since this V lambda plus 2 level of embedding was ruled out at this point, set theorists then started to look at large cardinal notions which are just below that level. So for example, a limit ordinal lambda and an elementary embedding from V lambda into itself. So that's just what's happening down here. This bit, V lambda, and we can map V lambda into itself for some limit ordinal lambda, or V lambda plus 1 into itself. And so these are large cardinal notions called I3 and I1. There's also an I2 in between there, which is another notion. And I0, which is, so I1 is stronger than I3. I0 is then a further strengthening of I1, but you're not allowed to go up to V lambda plus 2, so it's kind of in between V lambda plus 1 and V lambda plus 2. So L of V lambda plus 1 is the universe where you start with, where you put in all of V lambda plus 1, and then you add all the ordinals, and you sort of produce the smallest model of ZF, which contains that stuff, V lambda plus 1 and all the ordinals. So that contains some subsets of V lambda plus 1, so some of the stuff in V lambda plus 2, but it need not contain all of V lambda plus 2. So this is sort of just pushing close to the contradictory point of V lambda plus 2, but not quite there. So this is an elementary embedding from L of V lambda plus 1 into itself with critical point less than lambda. Okay, so in the picture, it sort of looks like V lambda plus 1, lambda plus 1, and then we add all the ordinals, and we just sort of get a very thin universe there, which doesn't, there's stuff in V lambda plus 2 that's missing from there. You embed that. All right. Okay, so these sorts of axioms have been now extensively studied for a lot of years by a lot of people, and there's been no contradiction found. There's a whole lot of structure there. I0 in particular exhibits a lot of phenomena that are analogous to axiom of determinacy. And so it looks like a very natural sort of system of axioms. I think most people think that they're probably consistent at this point because there's all this structure. I mean, it could be that all of this structure is just part of some very detailed, elaborate proof of contradiction in the end. So whether it's really, whether structure is really evidence that things should be consistent is a subjective thing. But anyway, there's a whole lot of structure there. Okay. So we're left with this question from Kunin's result that whether these statements can be proven without AC, without the axiom of choice, that there is no elementary embedding from V lambda plus 2 into itself, or there's no Reinhardt cardinal, no elementary embedding from V into itself. This has been an important open question. Well, the main result that I mentioned today is that essentially the answer to part 1 is no, that is you do need the axiom of choice to prove part 1. Essentially is because it's modular consistency of other things. So this is the result. So assume ZFC plus I0 at the ordinal lambda, and that there's a measurable cardinal strictly bigger than lambda. Then there's a transitive proper class model N, which satisfies the theory ZF, plus there is an elementary embedding from V lambda plus 2 into itself. And so this thing is consistent. This theory is consistent, so you need ZFC to rule out such an embedding. Okay, so that's what the corollary is. If you've got the consistency of this hypothesis theory that I0 plus the measurable above, then AC is necessary in Kunin's proof. Okay, so I said it. Essentially, the answer is no, because assuming the consistency of this theory, the answer is no. So, I mean, but if that's the case, then we can never. I mean, if it's consistent that if ZF plus J into V lambda plus 2 into itself is consistent, then one can never prove that anyway. One needs to prove it relative to, all we can do is relative consistency results by Gödel's theorems. Okay. Gabriel Goldberg here observed that the hypothesis measurable cardinal above lambda is actually unnecessary, so that really the correct hypothesis for the theorem is just ZFC plus I0 lambda. Also, in fact, the choice doesn't really matter, so ZF is enough itself. Brief mention, I'm not going to talk about the proof, but the proof adapts an argument of Wooden from lower in the large cardinal hierarchy. So there's sort of an important kind of argument from lower in the large cardinal hierarchy, which does a bunch of really interesting stuff. That adapts up to this level of V lambda plus 2 and sort of works here. Okay. Okay, so that's sort of this V lambda plus 2 level. But then there's also V into V and all these other things. So are large cardinals beyond this level consistent? So far, we don't have any variant of this V lambda plus 2 argument for V lambda plus 3 or higher. So there's no known consistency argument for embedding from V lambda plus 3 into itself, except some sort of tribute, unless you make it that sort of in your hypothesis, right? So in particular, from large cardinals consistent with ZFC, we don't know this sort of thing. However, a lot of people have investigated things like Reinhardt cardinals and large cardinal notions without the axiom of choice. There are these sorts of notions: Reinhardt, super Reinhardt, total Reinhardt, Berkeley, club Berkeley cardinals. There's a whole lot of structure there, like lower in the hierarchy. So it starts to look like this thing's consistent. We haven't found any contradiction. There's all this structure. It looks natural. There's continuing like analogs between properties here and determinacy notions that are appearing here as well. So there's a whole lot of interesting stuff. There's some other recent results above the level of V lambda plus 2 on embeddings from V alpha into V alpha, and I'm just going to indicate some of this to give you some more idea of some structure at this level. Okay, so so an old result of Suzuki is that working in ZF, in a sense, there is no Reinhardt cardinal. So Suzuki proved that if you require that all classes that you consider to be definable from parameters, which is one way of talking about what you mean by a class, and an elementary embedding from V into V is some sort of class. So he proved that there is no Reinhardt cardinal just in ZF, in a certain sense, that's when real classes have to be definable from parameters. So what he proved is that there's no elementary embedding from V into V, which is definable from parameters. So that means that there's no formula phi in the language of set theory and parameter or set p, such that this phi and p define the embedding, meaning that j of x equals y if and only if phi holds of p, x, and y for any sets x and y. Okay, so an elementary embedding cannot be definable over the universe, so it means so the elementary embedding has to be adding new information to the universe in some way that's like non-trivial. It's not built into the universe in some way already. Okay, so we can look at that same question for embeddings from V alpha into V alpha instead of V into V. So let's just say that an elementary embedding from V alpha into itself is parameter definable if it's like this. So if there's a formula phi and some parameter, some set in V alpha, such that J, this elementary embedding, is defined by those objects. So J of x equals y if and only if V alpha satisfies phi holds of px and y. Okay, so it's not V here, it's V phi here without anything. That just means V, the full universe, satisfies it. Here it's the structure V alpha satisfies it. Okay, so Suzuki's result is that there's no elementary embedding from V into V, which is parameter definable. Now we can look at V alphas as well. Okay, so first of all, a direct generalization of Suzuki's result is this one, that under ZF, we've got any limit ordinal lambda and any elementary embedding from V lambda into itself, then J is not parameter definable. Okay, so the V lambda here is any limit ordinal, so it's not, in Suzuki's result, you're working in the model of ZF. Here, it doesn't have to be a model of ZF, it's any limit. But it's the same result there in the end. Okay, so this is a limit ordinal. What about successor ordinals? Well, an easy calculation shows that if you go to lambda plus 1, where lambda is a limit, and you've got an elementary embedding from V lambda plus 1 into itself, then J is parameter definable. So automatically, you do have parameter definability at the first successor stage. So, and in fact, you can just use the parameter P, which is the restriction of J to V lambda. So if I've got a lambda plus 1 embedding into itself, V lambda plus 1 into itself, J here, and I just look at this part of the embedding acting on lambda, then that determines how it acts on all subsets of lambda by just sort of thinking about how it acts on all of the bounded subsets and putting them together. It tells you how it has to act on the full thing. So that tells you what the full J has to be. So that's sort of what happens here as a simple calculation. Okay, well, what about for lambda plus n into itself for n at least 2? This calculation doesn't obviously generalize to higher levels. Okay, and then a result joint with Goldberg is this, that if J from V alpha to V alpha is elementary, then J is parameter definable if and only if alpha is odd. Okay, so we saw at the bottom of the hierarchy, V lambda into V lambda, this result is limit ordinals which are even. This is never parameter definable. Lambda plus 1 into itself is parameter definable. And that switch turns out to go back and forth between even and odd all the way up. So V alpha into V alpha is parameter definable if and only if alpha is odd. So for some reason, there's this periodicity that comes into the structure of the V alpha hierarchy at this level. And in fact, the parameter, like for the lambda plus 1 level, when alpha is odd, we can always use this parameter, the restriction of J to the previous level, as the parameter to determine the next thing. But it's not. But the argument is different at higher levels compared to what happens at the limit stage. And this happens. So you've got this different sort of structure between the even and odd sides, even though at every beta it's just the power set of B beta plus 1 is just the power set. So there's no even odd periodicity built into the definition. These periodicity things are to do with the definability of elementary embeddings over these structures. Goldberg has looked at such periodicity, but in other properties like combinatorial properties in the V alphas that don't mention things like definability of embeddings and so on. So there's a whole. So these things are hoping to indicate that there's a whole structure in these things above the level of V lambda plus 2. Right? You don't see this periodicity until you get to lambda plus 2, right? You only have lambda and lambda plus 1, and V lambda plus 2 is just dead. So if you're working the expert choice, you never see this periodicity. You have to sort of move beyond there to start to see this structure. And one further remark, we had the axiom of determinacy proves certain fragments of the axiom of choice. Well, the same kind of thing happens here. Large cardinals at this level imply some fragments of the axiom of choice as well, but they rule out full choice. Okay, so in summary, here is a philosophical argument for the failure of the axiom of choice. Okay, so large cardinals arise as a natural organizing principle in the set theoretic universe. They have all of this structure and hierarchy to them. They're sort of in some sense, an extension of the ZF axioms. Certain properties of the ZF axioms up higher, and the axiom of infinity. It's the hierarchy is very graduated, and as in there's like, as I said, like between the axioms that I mentioned in the list, there's all these other refinements that go in between there, and you can sort of see all this gradual development in it. And it's linear, and that we can compare two of them. At least, I mean, that's not a theorem, but typically, given two large cardinal axioms, we can compare them and see one is above the other, and they fit together in terms of their consequences for the natural numbers, for example. There's a whole lot of complex and detailed structure below V lambda plus 2 and above there that continues. So there's this overall hierarchy that just V lambda plus 2 is just a point in the middle of, and it keeps going. And other than the Kunin inconsistency, there's no clear point where the overall hierarchy should stop in some sense. It just looks like it's a continuous sort of thing that goes on. Okay. There's this argument that measurable cardinals imply that V is beyond L. Well, measurable cardinals do imply that V is beyond L, that L has only countably many reals and so forth. And there's this argument there that therefore our conclusion should be that L cannot be the full set theoretic universe, so V is not equal to L. Okay, well, there's an analogous argument. Large cardinals, so instead of measurable cardinals, consider large cardinals at V lambda plus 2 or beyond. They imply that V is beyond the well-orderable universe. They imply that that axiom of choice fails, so there are non-well-orderable sets, so V is beyond the well-orderable universe, analogous to V being beyond L. And so our conclusion should be that the axiom of choice is false, by an analogy with this one here. Okay. So that's an argument for the failure of the axiom of choice. So, I don't know, it's up to you whether you buy it. Here are three scenarios. In part one, the axiom of choice is the correct principle in V, so the axiom of choice holds in V. Very large cardinals can only be exhibited in inner models of V, so very large meaning V lambda plus 2 and beyond, can only be exhibited in inner models. So, maybe you can have an inner model where axiom of choice fails, and that thinks that there are embeddings from V lambda plus 2 into itself, and so on. That would be analogous to the picture that under ZFC plus large cardinals in V, there are inner models that model the axiom of determinacy. We know that the axiom of determinacy is has a lot of features analogous to these large cardinal properties. So L of R, if you look at the universe where you've got all of the reals and all of the ordinals, the minimal model, that models determinacy under large cardinals in V. So that would be analogous to that. However, we have the problem that we don't yet know ZFC large cardinals that give us inner models with things like V lambda plus 3 into itself. We only get an inner model with V lambda plus 2 into itself. So we don't sort of have the picture of how to do that. So maybe that's just a big detailed structure that we have to understand that could be there. Okay, so that's one scenario. Second scenario is that large cardinals are the correct principle in V instead of the axiom of choice. So large cardinals including V lambda plus 2 and beyond there. That the axiom of choice was a historical accident. Remember that ZF the axiom of choice was somewhat of an outlier compared to the ZF axioms. So why did it appear there? Or maybe we thought it was correct initially, but now we've started to discover large cardinals as this natural principle, and there's this whole hierarchy, and by putting this spanner in the works, which is the axiom of choice, it breaks the hierarchy at this one point. So now we have more insight into the large cardinal hierarchy. And recall here that large cardinals imply fragments of the axiom of choice, so that maybe these are the more organic fragments that come from large cardinals. And also maybe the axiom of choice holds in some initial segment of V, like V lambda. And so maybe we sort of, by assuming the axiom of choice, we're cutting our view to this initial segment of V and ignoring what happens above there. Okay, so that's the second one. The third scenario is that there is no true V at all, and this whole discussion so far is predicated on that there's a true V that we're looking for. Maybe that's wrong, and maybe there's just many worlds, and all of these things are consistent, and it's just like consistency. Okay. And so I think that's the end. Thank you.
Thank you very much for a great talk. Any questions for the speaker?
So out of the three, which one you believe more?
Oh, I like number 2, which is the large cardinals.
Any other questions? I have a very naive question. So what do you mean by actually the third scenario? So what do you mean by having many boroughs?
Oh, many wells, like, there is no true set theoretic universe. There are just like a whole, lot of set theoretic universes which exist side by side, you could say, and some of them have some properties, some have other properties. They're just like a whole lot of, you view them as a whole lot of different mathematical structures, and there's no true one. They're all there.
Other questions?
Yeah. Yeah, there's no particular truth.
If there's no more questions, then let's thank the speaker again.
That's a fun topic.